Well, dear students, this is 18th lecture in the series of mechanics of metal forming. So far we have already discussed the yield criteria and basic stress strain concepts and stress strain at a point and related stress strain relationship, which is valid for 3-dimensional and all those things. In this particular lecture we are going to discuss plastic instability in metal forming, especially when forming is under 3-dimensional stress field. So, if you recall back, when a bar is subjected to uniaxial tension, it deforms almost very uniformly up to the point of maximum load, and then you will see that there is a necking takes place and resulting deformation is there non-uniform. A similar pattern occurs when in almost all deformation processes, you name any process, when the material is subjected to a tensile stress, and similarly under compressive stress conditions the failure occur by mostly by buckling or wrinkling that we would be coming across. Localized necking or wrinkling in formed parts are very often not acceptable from strength, functional and appearance consideration, because nobody would like to take a product if there is a wrinkle, if there is a something wrong, and that is taken as a in fact a defect one. Thus, the limit of useful deformation in forming is very important, and it is usually set by the extent of relatively uniform deformation. If the deformation is uniform, it is quite safe, it is considered. That is up to the point of necking or wrinkling. In fact, in ideal plastic material in which there is a strain hardening takes place, would become unstable in tension and begins to neck just as soon as the yielding takes place. A real material, however, undergoes strain hardening, which tends to increase the load carrying capacity of the specimen as deformation increases. Let us consider the case of simple tension, and if it is if you apply on both sides in the simple tension load P on a particular area A, mostly the middle area, the stress, that is sigma, can be calculated very easily by, that is P is equal to sigma capital A, and therefore for tension strain, if you calculate the strain in this tensile case, so that could be calculated if you differentiate this load P, that is which is given here in equation number 1. So one can differentiate it, so it becomes dP by d epsilon, and that would be simply the equal to capital A d sigma by d epsilon plus sigma dA by d epsilon. That is the simple differentiation. So for a continuously rising stress strain curve, if we take, so d sigma by d epsilon, that is the slope of this equation number 2, is positive, and d epsilon is also positive for a uniform tensile deformation. If during this deformation any cross section of the material is stressed more than its neighbor, it will have higher stress and further deformation in the section will not occur until all other sections have caught the strain in this section. Thus, for a positive load increment, that is, a uniform mode of straining is very required and it is all obtained. In fact, consider the case where the deformation during simple tension under failure load and that is when dP is negative. In this case, if the strain at some cross section becomes slightly greater than the strain elsewhere in the specimen, the load required for further plastic flow at this particular section will therefore decrease. This will result in the increased localized flow at the section and necking will occur therefore at this section. As the remainder of the test piece is unloaded, it is therefore follows that the load is maximum at the onset of necking, that is dP is equal to 0, and if you see the equation number 2, therefore can be written as capital A d sigma by d epsilon plus sigma d capital A by d epsilon, and this would be equal to 0, and this is shown here in equation number 3. Thus, necking in simple tension can be stated to occur when the ratio of increase in load due to strain hardening is just balanced by the rate of a decrease in load So, when the rate of increase in rate due to strain hardening is just balanced by the rate of decrease in load with area. Since plastic deformation causes no change in volume, if the volume is capital V, therefore we can simply write volume as A0 L0, where L0 is the initial length, and that should be equal to AL because the volume remains constant, and therefore it can be, if you differentiate this equation number 4 with respect to written as dV by d epsilon, and it will be equal to L dA by d epsilon plus A dL by d epsilon, and that would be equal to 0. Alright. So, let us take the figure number 2 here, where the surface is shown of the volume V. This is the surface A, and here the surface traction on this small element out of this particular surface ds, which is it is shown here. Nj represents the normal direction vector, and Fi is the forces that, and therefore delta ui is the displacement that would be the strain would be coming into, and therefore from equation number 5 it can be further written as capital dA by d epsilon, and which is equal to in fact A by L and dL by strain, and that is simply equal to, because minus A, and since if you see the d epsilon is nothing but dL by L, hence A and L are the cross sectional area in this equation number 7, and L represents the length. If we take O as the origin value, and if you consider equation number 2 and 5, so we can write down that d sigma by d epsilon becomes sigma, or simply we can write down 1 by sigma multiplied by d sigma by d epsilon, and this is equal to 1, and therefore this, if we represent it as 1 by z. So if this is represented at 1 by z, where the tangent at the point of instability, that is point I, gives z as the subtangent, it follows that the area of strain hardening is equal to the magnitude of the applied stress at instability. So if you look at equation number 9 here, this indicates that a tangent at the point of instability I on the true stress true strain curve, which is shown here in equation figure number 1, one can see here, will give the value of length GH as unit, and the strain at instability will be equal to therefore n capital Z minus capital B for a stress strain curve of the form which if you consider as sigma is equal to A in bracket B plus epsilon raised to the power n, if this particular curve is taken into consideration. So this construction, because the way it can be now plotted in this fashion, because it was first proposed by Consider way back in 1891, and therefore the name goes to Mr. Consider's, and this is how it is called as Consider's construction, and which is figure number 1. The necking condition discussed above so far, if it is considered in general form, so that the instability can be obtained in case of complex stresses, especially 3-dimensional stresses. So these generalized necking failure conditions, one can do it, and it has been derived by Hillier in 1963 around. So one can do this one, and therefore there are two, the first necking and second necking. So let us see what is first necking. So consider a plastic deformation of a surface S as in figure number 2 there, and if the same surface capital S, which is enclosing a volume V with the component stresses R traction Fi, if we consider, which is acting on the element small d, the surface. So if it is taken as surface as shown in figure number 2 earlier, and if the stress field is say sigma ij and nj as it is shown there in figure number 2 as the normal direction, the component that are directed along the outside normal to this small element of the surface ds, then Fi can be said as sigma ijn, and these are the conditions of equilibrium on the surface of the material. And if the displacement are shown as delta ui and change in the surface, the first necking condition for the onset of necking can be written as here in equation number 10. So that becomes d w, that is the incremental work, the infinitely small work, and that can be shown as to the over the integral for this particular surface S, that would be written as delta Fi multiplied by delta Ui ds, and that should be equal. If considering this particular equation number 10, and let us see the instability of a very simple case as tension. So, the axial load capital P and the displacement, which is delta U, are united across the cross section, and therefore the above equation, that is equation number 10, can be reduced to as shown here in equation number 11, that is delta W delta U integral delta Fi ds, and that is equal to simply delta U and delta capital P, which is equal to 0. So, this equation 11 gives the first necking condition. Let us see what happens the tube under internal pressure is taken up. We have taken lot of examples of thin tube under pressure to establish the yield criteria, one Mises and all those things cases. So, let us see here how can we understand the application of instability, especially the first necking condition. So, for thin tube under internal pressure. So, let us thin tube which has length L, having a radius R, and the thickness is, say, it is subjected to an internal pressure small p. So, if dl and dr are the axial and the radial displacement of the change in pressure delta p, so the first necking condition, that is deva w, and it would be simply given as pi r square delta p delta L plus 2 RL delta p delta r, and that should be equal to 0. The circumference, that is 1 and d epsilon 2 r can also be calculated, and that means deva as deva r by r, deva epsilon 2 can be calculated deva L by L, and L by deva r is equal to deva sigma 2 epsilon 2 deva epsilon 1 and multiplied by L. These are shown in equation number 13, 14 and 15 respectively here. So, if let us assume that the tube material to be yielding according to von Mises criteria, so the one can apply very easily the associated flow rule of the von Mises, and therefore it can be written as the d epsilon 1 divided by deuteric part of the stress in one direction would be equal to d epsilon 2 divided by deuteric part of the stress 2, and that would be further equal to d epsilon 3 divided by the stress in 3 direction, or simply one can then write down as d epsilon 2 by d epsilon 1, and that is equal to stresses in 2 direction, and denominator side it is in the 1 direction. So, for the thin tube is 0 almost, therefore one can write down this particular equation number 11, which is derivative part of the, it would be equal to sigma 11 minus 1 by third sigma 11 plus sigma 22, simply equal to 1 by third twice sigma 11 minus sigma 22. And similarly, the derivative part 1 by 3 and in bracket twice sigma 22 minus sigma 11, and therefore one can write simply d epsilon 22 by d epsilon 11, and it is equal to twice sigma 22 minus sigma 11, and on the denominator side it would become twice sigma 22, and this is what is shown in here in equation number 20. So for can be taken as PR by T, this is well known equation, and sigma 22 can be taken as PR by 2T, or simply sigma 11 becomes equal to twice of the sigma 22, and if you substitute this one in equation number 20, 22 by d sigma epsilon this d epsilon 22 by d epsilon 11 would be equal to 0, and therefore delta L would be 0. So if you use equation number 15 and this in equation 12, one can get very easily, that is dw is equal to 2r L delta P delta R is 0, and because delta R is more than 0, the first necking for the for necking reduces, that means delta P is equal to 0. The internal pressure is at the onset of necking, therefore, and this is what has been shown. The second necking start, to understand the second necking, let us take volume V again, which is subjected to stresses sigma ij, and let delta sigma ij star, if you recall back, be the change in the stress which satisfy equilibrium in volume V, the surface boundary condition on the surface capital L, and the yield criteria, but not necessarily the current rate of the strain hardening. If let us look at the figure number 3 here, where this shows the bifurcation of the stress path. So delta sigma ij star may therefore be considered a set of stress increment corresponding to the mode of deformation before necking. Delta sigma ij be the true set of the stress increment corresponding to the mode of the deformation after necking, satisfying the current rate of strain hardening, and delta epsilon ij, the tensor form, are strain increments at the onset of necking. The second necking condition can be written. So second necking condition, it is written as over the volume, that is the integral, this difference, that is the delta sigma ij minus delta sigma ij star. So that is what has been, the position has been changed, and then multiplied by delta epsilon ij be less than 0. So this has been shown here in equation number 24. When the stress distribution is uniform across the cross section in which to occur, in that case what will happen, that means this parameter, that is this factor, which is altogether delta sigma ij minus delta sigma epsilon ij, it should be less than 0. Okay. So, this is case. So, what happens? In fact, in simple tension, as we have already seen, P is equal to sigma A, and once it is the P is differentiated, we have already done earlier in equation in the beginning of this lecture. dP by d epsilon becomes A, and if it is plotted here, so this necking condition for the simple tension is plotted here in equation in the figure number 4 here. So, one can see here that this is what is the material stress strain curve, true stress strain curve, and I is the point of instability. So, and then if you look at the I point, so this is what Z we calculated earlier, and this is what is Z minus 1 from the I to the, where the tangent at the I comes and it hits at the strain axis. So, this is from the I, if you drop it here, this is Z minus 1, and this is what is the strain up to the instability point, and this is what one can find out from the instability point, the increment of the instrument. So, these two equation, that is epsilon star by d sigma star by d epsilon, and that would be simply equal to dP by d epsilon minus sigma by capital A d capital A by d epsilon. This sigma star by d epsilon is not consistent with the current rate of strain hardening, because when the strain hardening comes, it is the stress is going to change. The necking condition is simple in simple tension, therefore can be written very simply as here shown in equation 27. That means d sigma epsilon, it should be equal less than 0, and therefore if we substitute the value of these on the both side of the d sigma and d sigma star, d epsilon, and using the incompressibility condition, that means A, capital A, and that is cross sectional area, and the length, it should be constant all the time, and therefore one can write down here 1 by A dA by d epsilon 1 by L dL by d epsilon, and that should be equal to minus 1. If we consider is equal to dL by L, that is the strain increment. So, as indicated earlier, if you recall, the necking occurs when dP is equal to 0, that is the point where the necking occurs, and from the same point one can draw the tangent to the stress strain curve. So, that is when the applied load is 0, therefore, this equation number 29 can be written as here, that is 1 by sigma and dA by d epsilon, and that is equal to 1, and that is nothing but 1 by Z, what number 30. So, this result for which is the stress strain curve, where a tangent at the instability length, and the criteria under the critical condition criteria, if it is there, so as epsilon c, so it has been shown there. So at I, the strain increment, that is d epsilon, corresponds to the stress increment, that is d sigma, which is consistent with the current rate of the strain hardening. If instability does not occur at I, the stress increment will be therefore d obtained by drawing a tangent to the strain hardening curve I at I, and therefore clearly it shows that d sigma star is greater than d sigma and is consistent with the second. So now we can apply it for the instability under very complex stress, and where the three fields are instability under a very complex state of stress, and for the deforming material. The incremental plastic work therefore already used as dW is equal to sigma bar multiplied by d sigma generalized, that is generalized stress multiplied by generalized strain increment, and that can be represented if it is sigma ij and multiplied by d epsilon ij. Assume that the generalized stress is square to be a homogeneous quadratic function sigma ij, then at the yielding point we can write down that generalized stress is square minus twice f, f is the function sigma of the sigma ij. Concept of flow rule, if you recall, so one can, as it is the strain increment can be calculated as deva f by deva sigma ij d lambda, if you recall. So 33, then we can simply write down that the generalized stress multiplied by the general sigma ij and deva f by deva sigma I is 2 capital F d lambda, and that is simply equal to prime sigma square d lambda. Strain increment divided by generalized stress, and if you substitute the value of d lambda the flow rule, which is d epsilon ij, then it becomes is equal to d capital deva capital F deva sigma ij strain increment, generalized strain increment divided by generalized stress. Twice of the generalized stress multiplied by d generalized stress, and it is equal to twice by deva sigma ij and multiplied by d sigma ij. R's it can be so one can also write the same equation in this form, which is shown in equation number 39. R it can be written that d sigma bar multiplied by d epsilon bar, that is the d epsilon ij and d epsilon sigma ij. Similarly, for generalized stress, when the generalized stress is star, one can even write down in the same fashion, and therefore one can write down the equation number 41, and then we introduce the generalized stress star, so that becomes generalized stress star is square minus 2 capital F is equal to 0, and therefore one can write down that generalized incremental generalized stress, that is star, becomes if we take all together, it gives this value, that means d sigma ij minus d sigma ij star multiplied by d epsilon ij, and that gives your d sigma minus d sigma generalized and multiplied by d generalized strain increment. Hence, the second necking condition is all d sigma bar minus d sigma bar star multiplied by d the incremental strain, generalized strain, it would be less than 0. Second necking condition can be written, which is now shown here in equation number 46. That means d sigma bar minus d sigma bar star multiplied by d epsilon bar d sigma bar divided by d epsilon bar, its sigma bar multiplied by d sigma bar star divided by d epsilon bar. Since epsilon bar, d sigma bar and d sigma bar star are all positive scalar quantities, and therefore strain hardening curve, then from the considers construction, if you recall in figure equal to 1 by sigma bar multiplied by d sigma bar star divided by d epsilon bar, which is generalized strain. What is shown here in equation number 48. So, this is what is case corresponding to second necking, and it is valid for all the situation where the we would further continue this lecture in the second revise these things, because it will be easier for you to understand the second one. So, based on this, just like today one the thin cylinder, so I would like to thank you all for your patience and for listening. Very concept of the course of almost all the topics. It is you to practice. problems and whatever the instructions are given during the delivery of these courses, you also be very careful. Please mind that as much as you practice problems, that will make you stronger and stronger. Okay, so thank you all to uh, tell that you do not forget, please don't forget to give your feedback. So thank you.